Use the graph to answer each set of questions. So we want to first describe the transformation. Remember that when we're describing the transformation, we're describing from the root or parent function, which starts at 0, 0, to the new vertex point. And so I can see that this vertex has moved over to the right and down. What do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've moved to the right 2 and down 9. We can say a horizontal shift right 2 and a vertical shift down 2. Now the next thing we want to check for is, was there any kind of dilation? Well, we need to check to see if there was a scale used. So we'll start at our vertex, go up 1 over 1, up 1 over 1. Both of my ordered pairs end up at perfect intersections with the graph, which means the A value is 1. Since the A value is 1, there has not been a stretch or a shrink for this particular graph. Part B, write an equation in all three forms. Now, I tend to start with vertex form, simply because we have the vertex and we have no stretch. So our vertex form, f of x is equal to a times x minus h plus k. Oh, sorry, I left off my squared. So all I really need to know is the h and the k, which is the x and y of my vertex. So vertex form, we're going to have f of x is equal to no a value because we know it to be 1, x, and we want the opposite of our x value. Right now the vertex has an x value at positive 2, so we are going to subtract 2 because remember, whenever we're reading vertex form, we're looking at the opposite of the value inside the parentheses. So the opposite of negative 2 would be positive 2, which would match our graph. All right, our y value is negative, so we will say minus 9. All right, that wasn't so bad. Now, the other one I tend to prefer to be able to do, since we are in, since we're dealing with a graph, is intercept form. Now, the reason I like intercept form is, notice, we've already got our intercepts identified on this graph. They intersect at nice, pretty points. Well, since it intersects at nice, pretty points, we can go ahead and say f of x is equal to, all right, and again, these are going to be opposite values of what is the x value. So since it intersects at x of negative 1, x plus 1 is what we need for intercept form. Let's see, we got 1, 2, 3, 4, 5. Positive 5 is the intercept, so x minus 5 is the factor. Now, let's remember why these are the opposite. When I set x plus 1 equal to 0, remember that we would subtract 1 from both sides of the equation, and x would be equal to negative 1 as a root. As a factor, though, it's going to have its opposite value. All right, this gives us two options. We can either convert from vertex to intercept, from vertex to standard, or from intercept to standard. I'm going to go ahead and convert from intercept to standard. So let's take my x plus 1 and my x minus 5 and FOIL it. X times x is x squared. X times negative 5 is negative 5x. 1 times x is plus x, and 1 times negative 5 is minus 5. And we combine our like terms. So standard form is going to give us x squared minus 4x minus 5. All right, next question. What are the intercepts? Again, we've already identified the intercepts in our intercept form. We've already identified the intercepts on our graph. So the intercepts, x is equal to negative 1 and positive 5. Now, find the average rate of change from negative 1, from x is greater than negative 1 to x is less than negative 1. Now, this is another advantage where it's nice to have the graph. We want x is negative 1, so wherever my graph intersects that shaded line, to an x of 1, so wherever my graph intersects that shaded line. That makes things pretty easy when we're on a graph, because I can simply say from that point to this point, I want to know the slope of the line that connects the two. So we can use our rise over run. We've gone down 9, and we have run 1, 2. So m is equal to negative 9 over 2, and that cannot simplify any further unless we want to change it to a mixed number, which is not required. M is equal to negative 9 over 2. Question number 4. Describe the transformation. So again, we want to describe the transformation from the origin 0, 0 all the way over to our new vertex point. So we have had a horizontal shift right 7 units. We have had a vertical shift up 1 unit. All right, we want to check for any kind of vertical or stretch. So I'm going to start at that point, come down 1 over 1. I end up on the graph. So there has been no vertical stretch or vertical shrink. So let's write our equations. Again, I will start in vertex form. So vertex f of x is equal to, let's write down my vertex so I can see what it is. We have a 7, 1. So I want the opposite of my x value, x minus 7 squared plus 1. And that's not it for vertex form. Now for intercept form, we want to know where our intercepts are, which appears to be 6 and 8. And again, we're going to put the opposite values. So f of x is equal to x minus 6, x minus 8. All right, and then finally we want standard form. So we got x minus 6, x minus 8, and we want to FOIL. X squared minus 8x minus 6x plus 48. So my standard form, f of x is equal to x squared minus 14x plus 48. What are the roots? Again, we already identified the roots where the graph intersects the x-axis. And so that was at a x is equal to 6 and 8 value. Let's find the average rate of change from 5 to 6. So from 5, where does it intersect? And from 6, where does it intersect? We want to know the equation of the line that goes through these 2 points. So we would find our rise over run. M is equal to From the lower point, we go up 1, 2, 3. We go over 1. So our m value is equal to 3.